Hello everyone, welcome to the next meetup organized by quantum computing groups from Washington DC, Toronto and Warsaw. My name is Pavel and I will be the moderator today, and we have pleasure to host our great speaker, Dr. Javier Orduz, who is also a member of QMexico, so we know each other from QWorld. And today Javier will give a talk about mathematical foundations for modern cryptography in the quantum area. Before we start, just a few announcements. So, as you can see, this meeting is recorded. So, we are planning to upload a video to our YouTube channel, or actually, there is already a live streaming on YouTube, as far as I know. Is that correct, Helen? I think we have.
Yes, yes,
Yeah, we have the live streaming on YouTube as well.
yes.
And if you have any questions, please post your questions on the chat, and if there is a good opportunity, we'll try to interrupt and ask a question. And there will be a Q&A session at the end if we have time, because I know that we have a bit less time than usually. So before we proceed, I would like to announce our next event. So tomorrow, Professor Bakrzadeh will give a talk about and Samira Sayed Salehi will give a talk about decoding the quantum frontier, AI-driven error correction for fault-tolerant computing. Next week, Dr. Bruna Gabrieli will tell about compactifying the electronic wave function to quantum estimators for spin-coupled generalized valence bond wave functions. Then, on August 15, Dr. Seren Dak will tell us about theories quantum simulations with Rydberg atom arrays. Later, Harmeet Singh from IBM will tell about why quantum is ready now. And then in September, Dr. Dragos Manea will give a talk about Maze-free numerical method for Dirichlet eigenpairs of the Laplacian with potential. And in December, Dr. Yanjun Ji will tell about quantum deep learning, a comprehensive review. I believe there will be some other talks, some other meetups in the meantime, so before December as well, but we'll see. Okay, so with this, I will stop sharing my slides. And Javier, if you are ready, the Zoom is yours. So first of all, thanks for accepting our invitation. It's our pleasure to have you with us as a speaker, and we are looking forward to your presentation.
Great, thank you so much. I appreciate it. Just I'm gonna share my screen.
Okay.
Well, so yeah, as Powell, thank you so much. I appreciate the introduction. I also want to thank and acknowledge all the different organizations for this meetup. I know this meetup has maybe 5 years old or maybe more. I don't know. So this is really a huge effort because I know Helen's really active working on this. Powell and Sebastian, which is I don't know if Sebastian is here, but I know it is really interesting this kind of event. So thank you so much. I appreciate it. And well, so let's get the talk started. So we are going to talk about cryptography in quantum era, and particularly we are going to talk about some mathematical concepts. So I'm going to cover different topics, different concepts, focus on some on different mathematical concepts. Okay. Well, so to start, I want to discuss about this concept, cryptography. So as cryptography is actually a concept which is part of which is in cybersecurity and also cryptology, information security, and other similar concepts. Okay, so the first part that we have to know it's that cryptography it's part of one huge field which is called cryptology. Okay, and those two are different information security. So let me define the first one, which is cryptology. So cryptology is just an area or a field where we want to hide information. Okay, so there are different definitions. Actually, if you want to go maybe in a NIST, you can find some dictionaries and also different a list of concepts provided by the U.S. government. And then you will see that cryptology is cryptography is part of the cryptology. Okay, so that's important part. And the second part is that cryptography it has different definitions depending on which book or literature are you going to check, right? So I love one which is something like this. It's the science. It's the science. Okay, of secret writing. That's going to be our definition, and to hide the objective of this of define cryptography is because we want to hide information, right? That's the definition. But actually, you are going to say, maybe some of you are going to say, hey, that it looks a little bit incomplete, right? The problem is that here cryptography has or uses a lot of different mathematical concepts. So maybe we can also mention over here at any point that is the science of writing to hide information. Probably we can say using math if you want. Okay, that's something that we can add. As I mentioned previously, cryptography has different definition. Also, you can go NIST, this national and something standards from the USA. I know Europe and other different countries also and regions have different definition for cryptography. That's why you can find different definition. But we can mention at this point that cryptography is a science to hide information using math. Okay, that's that's okay. That's perfect. And additionally, as I mentioned previously, it is different to information security because information security is the protection of information and information systems from unauthorized access. Okay, there it has more details, more different things, but it's those three different concepts I'm gonna put over here are different. Okay, so cryptography, well, cryptology, and information security. Wow, that's okay. Okay, so we have 1, 2, and 3. Okay, those are very important, and currently we use these different areas in different fields as well. Okay, well, let's see. Now it's not working. What happened? Oh, okay. Well, but why cryptography matters? Why does cryptography matter? Okay, so let's see why this is important. Currently, why we are talking about these kind of things. Why we want to, maybe you are going to, you are wondering, why are we talking about these kind of things currently? And this is because we have to protect data. We have to keep our communication secure. And we also need to digital trust. So cryptography is relevant because we are going to protect data, which, as you know, we have a lot of different data in the websites, different, a lot of every day, every second, we are increasing this huge amount of data because we produce a lot of different messages. We produce a lot of different information in our bank accounts. Also, when we are using the transportation as well, we are increasing that number of information that it's a ton of information that we produce a lot. So the idea is protect data in financial areas, or as well, or personal information as well, And well, as I mentioned, institutional information, and then we don't want that people catch that information or get that or maybe get access to that information because they can use our information to do any kind of things, right? We have different examples. Um, Maybe I remember some years ago when we have this international attack, which was called WannaCry. That was really a problem, actually. Currently, I'm living in Mexico, and in Mexico, we had uh, during the time some different companies and institutions where people were had problems with this WannaCry attack, WannaCry attack, right? So that is a huge problem currently because we, as I mentioned previously, we produce a lot of data, a lot of information, and we don't want, or we want to keep that information secure. Okay, different kind of information. Well, so additionally, we have a digital trust, and we also use a lot the e-commerce, as banking information or banking account or bank accounts. We also have identity systems and integrity of modern society. We use this a lot. We actually as well we use the digital, or we trust in our digital systems because we use for different kind of things. For example, currently we have at UNAM, which is the university where I am working currently, and this is one of the most important universities in Latin America. Okay, so this is a huge institution. It has different campus around worldwide, actually, and so it has more than 500,000 of students. So it's huge, actually. So we use the digital systems or the systems or computational systems, for example, to create some tests, exams, or different courses as well. So there we also have information from the students, information for the faculty, and well, so we trust on those systems because we use every day. Okay, so that's why cryptography it's relevant. Okay, because we want to protect data, and we also trust in our digital systems. So and we want to keep those systems secured. Okay, well, let me mention about this another part, which is we want to keep our communication secure because we are going to ensure that our messages, when we are communicating, sending some WhatsApp messages or SMS messages, so we are sharing information. Some of them probably are information very important in particular, and we don't want more people get or catch that information, right? So that's why we want to keep those messages. We want to those remain confidential and unaltered between trust parties. Okay, so we want just if I send a message, for example, to Helen or to Helen or to Powell, so I want just a message was sent to Helen, which is going to be different a message to if I send it to Powell. So those two should be different, and I want to keep the confidentiality, right? And also, I don't want nobody change any point or any period or any kind of letter in the different those two different messages. Okay, so if I want just, for example, send a hi to Helen, I just want to say hi, not anything else. And I want, for example, to say hola, hello, Powell. Yeah, that's gonna be different, and I don't want somebody change that information. So we use cryptography, and I mentioned mathematical foundation, mathematical concepts, because with those we are going to protect sensitive data. We are going to keep our communication secure or enable secure communication and build trust across every digital transaction, which is important considering that currently we use the different apps in our phones to, I don't know, even to withdraw money or to send money to other body or any more people. And well, so we have a lot of different transactions, and yeah, we don't want nobody take that our money actually. Okay, well, that's why cryptography matters. Well, so the learning objectives about this particular talk, it's because are the following. The first is we want to understand some classical cryptography because, as I mentioned previously, the title of this talk is Cryptography in the Quantum Era, right? So now we have the classical cryptography, and we are going to see that we have quantum cryptography. Okay, those two are, well, we can say that it's the new one, which is, or the modern crypto, no, well, classical cryptography, modern cryptography, and quantum cryptography, those are different. So we want to keep classical and modern cryptography just in that one small ball, if you want, or box, and we want to keep this another quantum cryptography concept in another box. So the point with those two is that we were using classical things, algorithms, protocols, to do or to to implement different things to keep our information secure or data secure, etc. And that was when we were using classical things. Okay, so now under this new perspective, when we introduce quantum concepts, so we are going to create this new concept which is called quantum cryptography. Okay, so we will see that we have similar or things coming from the classical and modern cryptography, and we have this new cryptography with concepts coming from quantum mechanics and etc. or in actually physics. Okay, well, so and no, mathematical concepts as well. Okay? Well, so we are going to talk about this, explore some mathematical foundations and historical evolution and encryption. We are going to grasp quantum threats and learn how quantum computing undermines current security systems. We are going to explore post-quantum solutions, for example, discovering and emerging cryptography approaches that resist quantum attacks, because actually, considering that now we are working on this quantum computing, and we are implementing different algorithms and protocols and things in this new scenario where we work with quantum computing, then now we will have quantum computers, and then we want that when we have those new quantum computers, then we want those everything in our system, even if we have a hybrid system, then we want all of them to keep secure. Okay. Well, so this presentation it's focused on bridges, math, history, modern, and security challenges. Okay. Well, let me start with this part, talking about the from message to secure communication. Okay, so see, think that we have this message over here, which is a plain text, right? It is gonna be hello, right? And then we want to apply it. See, we have here one arrow along this direction, and then we have the first part, which is encryption algorithm plus key, right? This is important because we are going to, or we are mentioned right now, this key concept, right? We didn't mention previously. So just keep in mind, okay? So what? So after to introduce this key concept, this is relevant because now we have algorithm and key. Okay, this is for the encryption part. And then we have a ciphertext. Okay, keep in mind we have now ciphertext and now we had previously the plain text. Okay, those two are correlated, those are associated if you want. Okay, because see we have here the message when we have the plain text and we have over here the cipher text. Okay, so you can count 1, 2, 3, 4, 5 letters in a plain text. We should have the same numbers of letters 1, 2, 3, 4, and 5, right? Because we are, this is simple example. Okay, so because we are just associating one to each element over here, a new element over here. Okay. Let me see. Yeah, I'm gonna need one thing that I was behind my computer, so I'm gonna use it. Okay, so this is the ciphertext over here, and then we have an untrusted channel over here where we are sending the message, right? And then after pass this part on untrusted channel, then we have the decryption. Because if you want to think this was one guy over here, for example A, and this was a second guy over here, and this guy will have the message, right? But should be the same one, the same, because the message at the beginning and at the end should be the same, right? Even if we have a process over here which is changing, applying some transformation, maybe traveling along this untrusted channel, and after applying this decryption algorithm, okay? So at the end, recovering the plain text should be hello, which is the same over here, right? However, we have an issue over here because we thought that everything was clear, nobody was seeing or eavesdropping or messages. The problem is that usually there are people over here just waiting for this untrusted channel to catch the information and, I don't know, doing something, alter the information, changing some things, introducing some noise, right? Maybe extending the messages. Probably if this guy, an E, usually called as E, this guy take the message and he say hello world, for example, right? So it's different, right? It's different to this one. So it is changing the information, alter the information. Well, so that's how we have or we know that our communication works considering the from the message over here and after recovering the message, which is, as I mentioned, should be the same. Okay. Well, so the algorithm, let me mention something important over here about the algorithm. So the algorithm may be public. Cryptography protects information while it moves through an untrusted environment, as over here. And security should depend on the secrecy of the key, which is over here. That's why key matters. Because the secrecy, the security should depend on secrecy of the key. It means that our key should be just for me, just for the other uh, people who is getting the message, or but I don't want that my key might be catched by other external person, right? I don't want that because the key it's very important. Security should depend on secrecy of the key. So you want to you keep your key secure just for you. That's important. Okay. We are going to mention this in the next parts. Well, let's see. I don't know if there are. Let me see if maybe some questions or something in the meeting chat. No questions so far, so everything is okay, right?
Yep, it seems it's okay. Or maybe someone would like to unmute and ask a question. If so, please raise your hand.
Okay,
I think we can go on.
great. Thank you so much, Paul. Okay, let's see. So we're over here. Okay. Let's see. Okay. So yeah. Now let me just remember that we were talking about historical facts. So those are some of these. Okay, here. So this is an historical context, and this is about a 500 years journey which is called Albertus disk. I don't know if you can see this. Let me see. This is one Albertus disk. I hope you can see. Please let me know if you can do that. This is it. It is a Albertus disk. It has two disks actually. One smaller, which is this one, and one bigger, which is that. Okay, which is over here. Let me show you. That's Albertus disk. Okay, as you see here over here, it has the alphabet, right? So actually I can just uh, adjust this. I'm turning around and try to catch those to match the A's, yeah, over here. So this is the Albertus disk, and as you see, the capital cases are in the external or larger disk, and the lower cases are in the smaller disk, right? So I can just turn around, right? Yeah. So this is called the Albertus disk, and uh, this is very useful tool. I'm gonna show you. You can also see over here the Albertus disk. This is a different version. This is maybe more basic, right? I did it. I make this, so which is really fun when we are teaching this kind of things with to these different students. So they love doing these kind of things and also sharing some secret messages. So we're going to talk about this because it was invented by Leon Battista Alberti, and it was about 500 years ago. Okay, this is important because with this is cipher. We can say that we are going to use this as a cipher or encrypt information. We can use this is really simple, but we can create similar to this one as a polyalphabetic encryption, right? So it is really useful, and it was created by this guy some years ago, and he used the polyalphabetic cipher. Used multiple substitution alphabets, making cipher more resistant to frequency analysis. So this is another important concept that we are introducing over here: frequency analysis. Okay, just keep in mind that because we are going to mention the next slides. Well, so this is a mechanical device. As you see, you can just clockwise move clocks or counterclockwise, and it works. Actually, it has different math over here concepts, mathematical concepts over here. We are going to mention some of them, and it is a mechanical devices, two rotating concentric discs. It's over here. You can see. I hope you can find this template. I don't know. Just put on Albertus disk and download the PDF. Just cut it, and you're gonna get your Albertus disk. Well, so you can use this to encode and decode messages mechanically. Okay, Renaissance impact. So transformed cryptography from simple substitution into a more secure systematic practice. So as a legacy for this Albertus disk is that Albertus principles led groundwork for modern encryption algorithms and key-based systems. Again, our key and algorithms concepts that we mentioned previously are over here, or we recall those two concepts because those are important. We know that this might be public, but we don't want this to be public, okay? At least if we have only one key. This is about remember the frequency analysis that we mentioned over here. So on this part, you see this is just one example, and I'm going to mention a little bit more about that. So just let me say that here we are going to talk about the dynamic substitution and frequency analysis. This was the previous concept that we mentioned. And dynamic substitution, it's the new one where we are when we talk about dynamic substitution is when we change the substitution alphabet during encryption at frequency. Alberti, the guy who invented it, pioneered this idea by rotating those two cipher disk mid-message. So this looks really simple, and it means that you can hide information just rotating the smaller disk, okay? And that we call dynamic substitution. If you send a message and at any point, probably at the middle of the message, you change the key. I'm gonna show you. But if you change the key, then it means that you are going to rotate the disk, and then you will have a different letters associated to the new part of the message, right? And but why we are going to do that? Because we have this topic which is called frequency analysis. It means that you can do frequency analysis to the literature in general or messages might be might be I mean or messages might be attacked using frequency analysis, and that is because, as you see over here, for example, oh no, sorry, this one over here. In this case, this is just some numbers over here. I took actually this picture from this book, the code book. This is sync book. You can find, I don't know, in different websites. And this means that E is the most frequent letters or the common letters. Actually, E, you see E, T, A, and O. E, what is T? Yeah, T, A, and O. A, and O over here. Why? Because those have the highest bars, right? Okay, so common letters like A, T, A, and AO leave statistical fingerprints. It means attackers count symbols frequencies to reverse engineering the mapping. So, in other words, if we use or attackers use frequency analysis in a simple plain text, we can use frequency analysis and probably we can get the plain or the original message. And that's an issue, a huge problem, right? We don't want that all information might get in people who maybe are going to use the information to do any kind of things, right? Well, but wait. So we were talking about frequency analysis, dynamic substitution, but we don't know, or we want to know how substitution works. So each plain text letter is replaced by a fixed ciphertext, as over here. For example, I'm gonna again, what is A? Yeah, over here. Okay, so now this is my original Alberti's configuration, right? This is A and A match, and then we say that we are not rotating the disk. But if I want to replace a letter, for example, hello, right? Or not simple, hi, just H-I, okay? So I'm gonna just turn around. I'm gonna do this clockwise. I don't know. I'm gonna just do, let me move, yeah, the smaller one, okay? I'm gonna do just one, simple, right? And now, let me show you. If you see over here, a capital case is matching with Z, right? Lowercase over here, right? So I move just one, right? I turn around just one letter. So when I do that, and I'm gonna hide, remember, just say hi, right? I'm just going to, actually, I'm gonna do that. So I'm gonna hi, which is over here. This is the plain text. And I'm gonna, after moving or turning around one letter, just one letter, remember? So it means that now hi, let me find it. I'm gonna look for the H capital case, which is G. Let me see. I'm gonna try to show that. Right? You can see over here, right? Which is G. In my case, it's G. So now this is G, right? And I is H. So now the news or the ciphertext is just JH. That's it. And now we substitute the high, which was the plain text, to JEH, which is the ciphertext. Remember, we turn around the disk, the smaller one, clockwise, just one, okay? Okay, it means, I'm going maybe to move forward, it means that that is gonna be our key because we only turn around clockwise one letter, right? Okay, easy, easy peasy, perfect. So the same letter always maps to the same symbol, preserving the patterns, but we didn't change anything else. And as you should notice that the message is really short, right? It's just hi. And we didn't change or we didn't apply the dynamic substitution. We only keep the key as one. Okay. Well, that is how substitution works. Let me let me mention a little bit more about this breaking patterns, and it is because how it breaks, right? So repeating words, as over here, we remember we mentioned the O, and T over here, right? Those are repeated words, and letter pairs leak structure over time. That's it's simple because and also it's true because if you send the message using even the same key, which in this our case was one, and you just send a lot of different messages, eventually any attacker can do this frequency analysis, and then he's going to find, or this guy is going to find that you have a frequency analysis, and then probably he can get the key, and also if you don't change the key, so probably this guy can get all the entire amount of information that you sent, even if that was encrypted. But if you didn't change the key, so it's going to be just a similar frequency analysis over here, and then he's going to reproduce the new frequency analysis, but with under the new key value, which was in our case 1. Okay, so pattern recognition turns ciphertext back into plain text, which is something that over here, after this guy do this frequency analysis, or if he find the key, so he just go over here, find that the G corresponds to the H and H corresponds to I. So this guy is going to get all the information, okay? So the key inside static substitution, as we did previously, is vulnerable to statistical attacks, right? So eventually, this attacker can get the key value. Dynamic substitution raises the bar for crypto analysis. Okay, it means that if you send, for example, high power, for example, right? Power is over here, then this is going to be a different letter, right? I don't know, x1, x2, and so on. But if in this case you change, for example, k2, so this part of the message is different to this one, and then you are applying some dynamic substitution. This is a simple example. Actually, you can find a little bit more complex substitution examples. Okay. Well, let's see. Okay, let me see question. I don't see any questions so far. So let me mention about this part, the algorithm. Remember that we have those two different components, the algorithm and the key. So should the algorithm be secret? Well, actually, we have a Kirchhoff's principle, which states a crystal system should remain secure even when everything except the key is public, right? So again, we don't want that the attacker get this number because it's our key, right? We want to keep that secure. We want to keep that private. That's why currently there are different initiatives and projects and algorithms to keep the key secure. Okay, because everything. So it means that even the algorithm might be public, right? So we have to protect the key. So this is the secret algorithm, secret key, but we have a system security, right? And also we have on this side, on your right hand side, we have the public algorithm as going to be associated to the secret key. And even this, we will have a system security, right? So the algorithm might be public. Yes, the algorithm might be public. The problem is that we don't want, or the main issue is that we want to keep our key secure. Okay. Well, I don't know if maybe somebody was open and was on mute. So let me know if there is any question, please. Is there any question?
Yes, would someone like to ask a question? All right. I think we can continue.
Okay. Okay. Thank you, Paul. Okay, great. So let's move on and then talking about math. Remember that we mentioned that this Albertus disk has math? Yes. And we call that sometimes clock arithmetic. Okay. So numbers wrap around a fixed models like hours on a clock face. Similar to this, if you check this Albertus disk, it's like a clock, right? Well, so it has the math and the math in this for this kind of things or tools are called clock arithmetic. Well, so we will use this definition, which is a congruence relation over here, A congruence V module N. Means A and B share the same remainder when divided by N. Okay? Let me see, maybe we can I think maybe we have an example. Let me find it. Yes. Oh, yeah. I have one simple example. Let me open over here my. Well, so for example, I'm gonna put over here the example. Think that we want 26, which is gonna be n. Okay, 26 is gonna be the value of n. Why 26? Because we are referring again to this Albertus disk. And if you count this, we have 26 elements. This is for one alphabet. So if we want to encode or encode the information, we will have a function similar to this. A function encryption, which is depends on key or K, and X is gonna be our plain text. So we define the congruence relation X, which is the plain text or the element of the plain text, plus key, which is gonna be K, which is gonna be the key, and then we have module 26. Oh, sorry. Let me see. I can move it. I don't remember how. There you go. Okay, 26. Right. This is, we can use this notation over here, yeah, just to keep this over here. There's the same one. And then we have here the function to encrypt information using the Albertex disk, right? Let me show you, but because maybe you are wondering, hey, hey, Javier, if we have encryption function, we have a decryption function. Yeah, of course, that we have the decryption function, which now is going to be Y, because Y is going to be the encrypted information or the cipher information. Then we have Y, which is going to be the encrypted information. Oh, yeah, and here it's going to be minus K, right? Because now we are going to do the inverse operation. And then we have over here module 26, because it's the same, actually, right? The model has to be the same, right? And then we have the encryption and the decryption functions over here for one just a simple tool such as this Albert disk. Well, let me move on because yeah, those are the basis for the encryption. This is one of the most simple functions. There are others, but this is one of the most simple functions using module or congruence relation. Sometimes we can also define the modular exponentiation forms, which are very important or are the core of many modern cipher systems. Okay? Well, so congruence relation let us work with finite number spaces, making complex encryption operations computationally feasible. Okay, this is a little bit more, not too much, but a little bit more complex example using again the encryption and the decryption, right? So you can make this your Albertis, you can use your Albertis disk, and then you will have, for example, this plain text that this is going to be like some steps, right? So here we have start with a readable message such as hello. Key selection, it means that you turn around, I don't know, clock or counterclockwise, usually clockwise, and people check, in this example, we can use K equal 3, and then you have now the encryption because each letter over here we have a different one in the new smaller disk, right? Or in the smaller disk. So you have here the plain text, right? Hello. Oh, sorry. Uh, oh, yeah, I missed one. I'm sorry. Yeah, this should be twice, okay? And then, yeah, and then this one. Okay, so we have here is gonna be K, yeah, K H O O R. That's, oh yeah, there you go over here, right? That is gonna be your ciphertext. And the decryption reverses the shift by subtracting key to recover the plain text as we did over here. If you want to apply or if you want to decipher the message, just use this function over here, right? Okay, we use these kind of things usually in a communication between the 2 points, A and B, right? And we have here, we apply the keys to encrypt and to the decrypt. But the plain text at the beginning and at the end should be the same, okay? Well, so we mentioned previously the modular arithmetic or congruence relations or reminder operations. Sometimes those are different concepts associated to arithmetic or modular arithmetic, right? Well, so the goal with these things that we previously do over here, that we were doing over here, and also over here, was because we want to transform the plain text in a ciphertext to protect information from unauthorized readers. Okay, so what we are doing so far using math to transform information. That's it. That we are using. Okay. Well, so let's see. Why matters? Why it matters? Key space and security. Okay. So considering that we have a key a 128-bit key, and it has 2 to the power 128 possible combinations, right? So if we want to make a brute force to attack computationally infeasible with current technology, that's a fact. Actually, if we have something like that, that make brute force attacks computationally infeasible with current technology. If you increase just one, where I put that, I don't know. Yeah, over here, exponentiation grow. So every extra bit doubles search space, raising the cost exhaustive search. So if you increase one bit over here, then this is going to double the search space. Okay, that's good. I mean, you can say, oh, yeah, we can just increase the number of our bits and that's it. Well, the problem is that when we increase that, we are going to use or to need more computational resources, right? That's an issue. Well, actually, you can also keep the key length longer because it is going to be exponentially uh, important because it increases the number of possible keys an attacker that an attacker must test, right? But again, if you increase randomly the number of or make the key length increase it and just make it larger and larger, that eventually is going to impact in your computation, in your computational computing resources, right? Well, we hello, can you hear me? Something.
Yeah,
Hello.
we can still
Yeah.
hear you.
Thank you, thank you. Okay. Well, so we also can use brute force attacks. We mentioned previously over here, right? Force attacks. And brute force time depends on key size, available compute, and attack parallelism. That again, we mentioned over here, it depends, brute force attacks depend on our computational systems, right? Depending on the key size, right, as over here, and the attack parallelism. It means that we can increase the number of computing or computers, and then probably we are going to reduce time when we are attacking a system, right? That's good, but sometimes it's not efficiently correct, okay? Because we are going to increase the number of computers, people who are going to work, maybe, well, if we just mention a lot of kind of things, for example, energy, power that we are going to use, then everything is going to zoom and increase or the things that we have to invest to just to make a brute force attack. Well, security metrics, so security is measured by the computational work needed to break a cipher. So it means that, again, you use a lot of different computational or computational resources, then you are going to increase the value or the invest that you are using just to break a cipher or a system, right? Well, so right now we have different or two different scenarios talking about cryptography. One is symmetric cryptography and the other one is public cryptography or asymmetric cryptography. The first one uses a single shared secret key. Remember we mentioned the keys? Well, so that's only that uses, it uses a key, a single shared secret key, which is shared between A and B, for example, over here, or A and B, right? It is fast and efficient for bulk data and requires secure key distribution. Okay, so it means that if I have a key over here, I need a way to send the key over here, and then this guy should get the key, but nobody else, right? So I have to find a secure key distribution, okay? Well, It is simple. It is okay. It works good for some scenarios, which is good, right? But also on the other side, we have the public key cryptography, and this uses a key pair, public and private, enables secure exchange without meeting, slower but scalable for open networks, and well, so that's those two different scenarios. So we have key differences, and those are, the first one, we have a private key, and in the second case, we have, I'm gonna try to increase size. Let me see if that works. Yes, that works, okay. So here you have the message, right? Oh, actually, notice that over here we have a key 5 graph, right? You remember this is from math. We have a key 5 graph. So it means that all of them here as well, all of them, each pair has a connection, an edge, right? So those are the different nodes, right? Or vertices. We have 5 vertices. Well, so we have a message over here, we have the public keys over here, and each of these we have a secret key. So this guy will have a secret key number 3, secret key number 2, 1, 5, and 4, right? For example, actually over here. Each of them will have this paired. Additionally, it also will have this public key, right? Well, okay, so if we compare those two scenarios where we have public and symmetric and asymmetric cryptography, then we have symmetric systems are ideal for encrypting large volumes quickly, and public key systems solve the key distribution problem at a performance. Okay, because now we have two keys, public, and each of the different vertices or persons or people will have one different key, okay, which is the secret or private key. Well, one important concept in cryptography, which is these one-way functions, okay? That one-way functions means that we want just functions that we will have this important property. It's easy forward, hard backward. It means that if we have um, over here, and let's see, yeah, choose, well, if we have, somebody can change, can see can send the message, right? It means that apply encryption, and then the other, on the point B, that guy will have the information, right? But that, when this guy is going to get the information, let's see, so for example, this is point A, right? And this is gonna be point B, right? Sorry. Okay, this guy, point B. So this guy has to apply an inverse function, as we see previously, or an inverse process, to get the plain text, right, or the original text. So we want to make this inverse, as we want to do that hard, right? Why? Well, just for people who don't have the keys, right? So this is the process. We have or choose two primes numbers, P and Q, right? And then do this, I mean, getting n, it's easy because we are going to multiply those two prime numbers. And then we will have the public value, which is n, right? And that is easy. We just calculate n doing the product between those two, right? And then recover P and Q. However, that's easy, but it's computational difficult. That is that we want with this one-way function. We want to make this computational difficult to get or to do this direction, this or doing these steps or following this path along this direction. We want to do that difficult, right? That's the point with this one-way functions. That we call one-way function. We want just functions which is going to be easy to calculate, and it's going to be a public value, but we want to make difficult or computational difficult making the reversal process. Okay. This is another important and similar concept to the one-way function, which is trapdoor function as well. That's another name that people sometimes call this one-way or trapdoor function. That's alternative. Okay, it has a theorem. We're not going to discuss right now. Just skip, but you have right now the idea. Okay. Okay, so public key cryptography, sometimes called as a PKC, relies on mathematical operations that are easy to compute but difficult to reverse without secret information. So notice that here we want to get this kind of systems. Oh, wait, somebody open. No? Oh, let's see. Oh, well, yeah. Okay, we are going to discuss. Okay, there are some comments. Okay, I think we are going to. Okay, I'm going to stop at eventually. Just let me finish. Actually, I thought this talk just for 1 hour. Okay, so I'm going to stop in 5 minutes, I think so, and then we are going to go to the discussion. Sounds good? Because I have a trip upcoming. Okay. Well, so yeah, we were talking about this. And then this is another concept that we use currently, which is RSA intuition. And the core idea is that we use prime factorization because that is actually that we are doing over here, right? Those two are prime numbers, and we are going to use prime factorization. So with that, those concepts are used in a lot of different crypto systems, okay, or modern crypto systems. Well, so we use prime factorization. We want to, or we introduce those two concepts, public and private keys, where a public key encrypts message and a private key decrypts as in secret prime knowledge. And mathematical trapdoor function or one-way function as well. So it's to compute in one direction, yet practically impossible to reverse without the secret key. Okay. Why it works? Because RSA security relies on the difficulty of factoring large integers, making brute force attacks infeasible with classical computer. It means that RSA is relying on difficult factorization or factoring. Okay. Well, um, let me quickly just make or introduce this quantum computer over here. And it is considering that we have this Shannon entropy. There is one similar to the Shannon entropy in terms of the quantum computer, which is the von Neumann entropy, which is similar to the Shannon entropy. Both are in terms of the probabilities, but in the for the von Neumann entropy, that consider the density operator, which is one operator coming from the quantum mechanics, or well, it's actually a study. Mechanical statistics, which is the things where the field, well, the different quantum concepts, but considering that these quantum concepts, mathematical quantum concepts coming from a linear algebra and probability are coming. So those different concepts are coming from the mechanical statistics, okay? So that is, in that area is where we define the entropy. So when we talk about the quantum entropy for the information, we call that von Neumann entropy, okay? I didn't put that over here, but it's similar to the Shannon entropy. That's very important in our crypto systems. You know more about, you have some facts about cloud Shannons and what. So let's see, I'm gonna skip this one. This is about the definition for the qubit. but we know that I know I mean usually people who attend these sessions knows a lot about different quantum computers. I'm going to skip this really fast because you know as how it's a qubit and the definition for that as well. This is similar as well. We have the qubits, gates, and quantum parallelism, which are different concepts that we use in cryptography. Considering this scenario where now we are introducing the quantum computing or the quantum information in the cryptography field. So these are the fundamental things. You know that we have different gates, different concepts such as parallelism, and which also those are coming from the quantum mechanics and mechanical statistics and probability and statistics. Well, why source algorithms change everything? Well, as you know, um, the algorithm can factor integers and compute discrete logarithms in polynomial time, undermining the mathematical foundation of RSA and elliptic curve cryptography, okay, which is over here. Polynomial time, it is okay. I mean, in terms of computational complexity of theory, it is important because it help or we want to have some polynomial times algorithms in order to solve integer factorization exponentially faster than classical algorithms. Well, so with this, we can break with the short algorithm. We can break the RSA. We can break elliptic cryptography and timeline concerns are, for example, one is cryptographically relevant quantum computers may emerge within decades. Well, I'm being optimistic. Okay. Okay. So let's see. Oh yeah. So I'm going to let's see. I'm going to stop over here. I can also share these slides because as I mentioned previously, I'm sorry I have to leave because I have in less 1 hour a trip which is upcoming. But I would like to promote the discussion maybe for 10 minutes if you are okay. Please, I was checking. Let me see.
Yes. All right, let's see if there are some questions on the chat. There are some comments, but I do not see questions. Maybe someone would like to unmute.
Hi, can I ask
Okay.
a question?
Yeah, sure.
Yeah.
Yes, Katania. It's very interesting. It's good learning here about cryptography. My question, when you talk about the public key encryptions, you mentioned about prime numbers. I wonder how often are the complex prime numbers or complex hybrid numbers and traditional prime numbers are used in encryption.
How often? Could you maybe
Yeah, I was talking
restructure the
about
question, please?
you talk about the prime numbers in the public encryptions, and
Yeah.
I was wondering about the complex prime numbers,
Oh, got it. Got it. Okay, got it.
and how often complex numbers, prime numbers, are used in encryption and hybrid, complex
Uh-huh.
prime
Uh-huh.
numbers and traditional prime numbers.
Uh-huh. Okay, that's a interesting question considering that this is a scenario when we introduce the quantum computing. So in that case, we are able to introduce complex numbers because actually that's part of the definition in quantum mechanics or in quantum things, right? When we introduce quantum things in general mechanics or physics, quantum mechanics or quantum physics, we allow to have complex numbers. I think, well, now it's the part is introduce complex prime numbers, right? So that is really important, and actually that is part of the that people are doing or exploring in different areas. That is really good because now when we introduce this, we also introduce the mathematical concept, which is um, the Hilbert space, where we now are working with these kind of things, right? So It is important right now. Yes, people are working on this. Yes, there are different papers and things that people are working or showing how to use or introduce these concepts in cryptography. I don't have right now one application to mention, but well, so maybe in the future we can talk about that. But it's an open field where people are working, right? So that's my short answer, and I hope that works.
Yeah, thank you. Thank you for your answer.
Thank you, Ketano.
I had a quick question about the terminology. I hear the asymmetric key often, and I just want to make sure that that is the same as public key, correct? Because the symmetric key is the private key. Is that right?
Yeah, yes, I mentioned that over here. Yes. Yeah, we have those two, symmetric and asymmetric keys. Okay. Actually, I mentioned that as a cryptography, symmetric cryptography and asymmetric, and public symmetric key. Sorry, public key cryptography.
Thank you.
Yeah. Thank you, Jordan. Oh, I was checking the message, the chat, meeting chat. Let's see.
Yes.
Do you want to check any particular Powell or?
I'm just also reading the
Ah,
comment.
okay, yeah.
There are
So
mainly comments, so I'm not sure. Yeah. Maybe
yeah, yeah, yeah.
someone, maybe someone else would like to unmute.
Oh yeah, sounds good. So thank you, William. I was checking. I'm gonna open that PDF. I think it's the one PDF document. I'm gonna open it. I don't know. It is. It's gonna book in PDF format. Okay, I'm gonna check. Thank you so much, William, for sharing that. Yeah, got it. I'm
Okay,
looking for this book.
Javier,
Yeah.
as you know, you are in a rush a bit, and I think we can just finish. It doesn't seem that there are more questions now, so
Uh-huh.
I think we can just conclude.
Okay. Sounds
All
good.
right. Javier,
Yeah.
thank you once again for the great presentation and answering the question that we had, and we look forward to host you in one of our next meetups, of course, in the future. Maybe they will have more time, and then we can follow up and or just cover some other topics.
Great. Yeah, I see people sharing the emojis. Thank you so much, the
Thank you.
reaction. I appreciate. Thank you again, Paula. Thank you, Helen, and thank you everyone for being here. Thank you for the invitation, and I enjoyed the time talking about this kind of things, and open to
Perfect.
talk and discuss and collaborate about potential projects. Okay. Thank you.
Great. Thank you. Thanks, everyone. Thanks for coming.
Thank you. Bye bye. Have a good day.
Bye bye.
By the way, if we still have plenty of time, so if you want to discuss, please go ahead. Yeah, we can discuss among ourselves. I know Jeremy has a lot of comments and questions.
I don't know if someone would like to discuss something, then this is okay for me, but
Yeah. William, you raise your hand.
Sure. Ron Schneier was kind enough to let me speak at our Chicago Quantum Group last week. And so I made two quick presentations. One of them was on the paper that I put together about the state of quantum in the USA. And it's got about 10 or 12 slides. And then you have to go down into the presentation and see the whole thing. It's really interesting. And then the second presentation was on Harvest Now, Decrypt Later. And there's a couple of things that are shared in that presentation you won't see too many other places. One of them is a lot of people don't understand how big the PQC problem is and how many devices are going to have to be reconfigured to make them quantum safe. I did a lot of research on internet connected devices, and just think about these two numbers. There's about 8.5 billion people in the world, and about 2/3 or 3/4 of those people are connected to the internet. The number of devices that are connected to the internet that are going to have to be reconfigured is about 61.7 billion. So almost 8 times the number of people on the planet. So it's an enormous number. And the other thing I included in the presentation is 2 examples of what an HNDL attack might look like. It was based on the idea of the Enron email data capture that was captured back in 2002. And that data was used to successfully send some high-level executives to prison to get successful convictions and send them to prison. The other one is as recently, I think, as May of this year, May of 2026, when they started disclosing the Epstein documents out of the Epstein files, and a guy's name came up as having a lot of vulgar but very chummy emails with Jeffrey Epstein, and it was a guy named Peter Attia, who's actually supposed to be a longevity expert, and he's published on longevity, extending human life. But the day before that disclosure, or the same day of the disclosure, he was given probably a high, I don't know, 7-figure job with CBS. And when this saw the light of day, he was terminated the very next day. So the moral to the story is, when data that's supposed to be confidential and protected by classical encryption, it's no longer relevant. It can be popped by things like Shor's algorithm. There's going to be a lot of nervous people out there in the world when they're getting their secrets revealed, and a lot of bad things are going to happen. And I've actually discussed this with some people, and I said, do you think it'll happen all at once, or do you think it'll just trickle in? And most people think it'll just trickle in, and you'll see news blurbs about people knowing about stuff that they don't have any business knowing about. So the world is about to get a lot more interesting, and I'm excited to see people wake up. I don't think they're all waking up on the same scale, but people are waking up about the urgency of PQC.
Hey, is it okay if I say something?
Sure,
Yes,
sure.
please.
Hey, well, first of all, Jeremy Swenson here. Thanks so much for putting this together. A lot of good information and good chat in the chat thread there from Peter and other folks, William as well. The one thing that that interests me is this speed of AI, and AI being used to break the older algorithms. And so that's something I don't think was fully addressed in this conversation. I have a new book coming out. It's a peer-reviewed book. It's an academic publisher, CRC Press, out of the UK, part of Taylor and Francis. It's a 400-page book, 550 citation, 24 infographic, and I got a lot of big name endorsers. So I would like to introduce myself to this group to perhaps be a speaker at one of your future meetups. The book isn't out yet. I have a lot of articles that are kind of a precursor to this book. But yeah, so I just would just drop that if you're looking for a future speaker to kind of cover this topic. The book covers AI, cybersecurity, digital strategy. It's written from a business sense. It's not designed to throw somebody off at all. It's for that business leader, that CIO, that CISO, that board member. That's the perspective that it's written from. And like I said, it's almost done. I've been working on it 2.5 years. But if you go to my LinkedIn, you can see some of the articles that I've written. Like I said, are a precursor to the book.
I just add you on LinkedIn, so I reach out to you. You can add me, and then I'll reach out to you to be the speaker.
Would love to do it. Happy to pay it forward. You guys have a really good group.
Thank you.
Sure.
And I noticed Ron raised his hand. Is Ron, do you have a question? And also, Ron is not talking. Okay. During the meantime, Peter has a question. I didn't realize source could break ECC. That was new to me. Would anyone want to discuss that? So can anyone discuss source algorithm can break ECC? So he want people to discuss about that. Okay, Peter say no worries. I'll go down the rabbit hole. And I realized there's a question on YouTube. I finished my master in quantum computing, but it's still somewhat unclear to me how to transition my profile to work on quantum cryptography. What would be recommendation you may have? There's a question for the participants. So if you have any suggestion for him, we can talk.
Can you hear me now?
Yes.
Apparently I bumped the mute button on my headset. Hello, everyone. I just got a comment about today's presenter. I would hope if you arrange to bring him back, that what I would think the group would find interesting is doing a little bit more deep dive on what the potential or what the recommendations are for quantum resistant encryption algorithms, are how they work, and why people believe they're going to be quantum resistant. I noticed he spent most of his hour talking about the basics of cryptography. I'm sure there's some people here today that benefit by it, but I think this group probably understands most of that. Two-part keys. I mean, if you're involved in quantum, you hear about this part all the time. But what I would like to see is somebody who's really invested in the cryptography of the quantum resistant candidates, and drill down on it and try to figure out why they think they might be resistant. So that's just a comment I had.
Mm-hmm. Okay, perhaps I can here try to give a comment. Actually, I can try to give comments to all the questions and comments that haven't mentioned. So starting from the last one. So there are several approaches to build the so-called quantum resistant algorithms or post-quantum cryptography algorithms. And as far as I know, if all the cases that we know, there are no formal mathematical proofs that quantum computers will never break these algorithms. The thing is that we just do not see that any of the quantum algorithms that we know can really break these post-quantum cryptography algorithms. So that's why we believe that it will never happen, but there are no mathematical proofs for this. Regarding the previous question about Shor's algorithm breaking ECC, this is true as far as I know, because the Shor's algorithm can be used to factorize large numbers, and the assumption that the factorization problem is difficult was was a foundation of the RSA algorithm, for example, right? But actually, what happens in the Shor's algorithm is something that's called quantum Fourier transform, and it can be used to not only factorize large numbers but also solve the discrete logarithm problem in finite fields, and including elliptic curves, which can be used to break the ECC, as far as I know, in polynomial time on quantum computer. And regarding the last question or comments about transitioning from quantum computing to quantum cryptography. So if someone has a background in quantum computing, then I believe that a person should already have good or sufficient background in quantum mechanics as well, and in general quantum mechanics and quantum phenomena like the entanglement and superposition are also the fundamental of quantum cryptography and quantum communication, quantum key distribution, right? So we still use quantum phenomena to implement the quantum cryptography. But what's important to know is that quantum cryptography is something else than post-quantum cryptography, because the post-quantum cryptography algorithms are classical algorithms, actually, as for now at least. Maybe in the future we'll have quantum, post-quantum algorithms as well, but as for now, all the well-known and standardized post-quantum cryptography algorithms are classical algorithms. So the quantum computing is not as useful there in the PQC domain. Rather, mathematics like algebra, mainly algebra in my opinion, and number theory, computational theory, some computational complexity, something like this. So in general, background in computer science is needed more than the background in computer science and math, more than the background in physics in case of PQC. But in case of quantum cryptography, like quantum communication, you need a background in physics and quantum mechanics, some good understanding of the entanglement, superposition, and some other aspects of quantum mechanics. All right, I see a comment from Jeremy. And there's another comment from William. Yes, William, please.
Yeah, a lot of people said this was hype. I'm not really sure, but apparently there were some alarming figures that came out this week about Claude pounding on one of the four approved PQC algorithms. And for the uninitiated, when NIST declared the competition, I think back in about 2016 or 2018.
Yes.
Yeah.
I think it was around 2016.
Yeah. So I guess there was something like 84 entries, and at the end of it, they had four approved quantum safe algorithms, which is great. And also for the uninitiated in the crypto world, one of the worst things you can ever do is try to develop your own cryptographic algorithm and use a custom cryptographic algorithm. Everybody says it's the worst idea in the world because I love the Snowden quote that the NSA can do 8 billion cracks a second, So most people don't have the superhuman powers to develop sound cryptography algorithms. We have to use the ones that people like NIST come up with. But my quick question was, what do people think about this Claude thing using 60 hours of compute time to find weaknesses in this PQC algorithm, and I forgot the name of it. I know it's not Falcon; it's another one. But they found it and they declared victory. And I a couple of weeks ago or a couple of months ago, I came up with this phrase: all encryption has a shelf life. So just about the time that everybody says, "Oh yeah, we've got these new airtight algorithms," just sit back and wait, because I told somebody earlier this week, I said, most of us that are reading this will live long enough to see all these master encryption algorithms that NIST has approved. They will be cracked. And so the answer to this is you have to make your enterprise crypto agile. Crypto agility is going to be the big buzzword for the next 1 or 2 years when people finally figure out how to do it right. But you're going to have to be crypto agile, because the bad guys are going to use sophisticated AI tools and break the ciphers that everybody thought were bulletproof. They're going to break them at a much faster rate. So we're going to be chasing our tails if we don't get crypto agility down well.
Yeah, it can be interesting. So in general, our future will be interesting, and I'm particularly curious how AI will impact this whole post-quantum cryptography domain. So both in terms of designing better algorithms and better ways to tackle them. So we'll live in very interesting times, definitely. Many important things will happen in the next few years, I believe. All right, do we have more questions or comments?
Yeah, I can stay if you are ready to take off. You can take off, but I can stay if you have
All
more
right.
questions to discuss.
I can still wait for a couple of
Yeah.
minutes, so
Sure.
let's see.
Jordan has a question. How much was the Jackson Nano V2? He's talking about the NVIDIA Jackson Nano V2.
When I bought it, it was a whole $100. I bought it at Micro Center here in Chicago, and I think the multiplier is billion, but it may actually be trillion. I have to double check that. And it's only slightly bigger than a Raspberry Pi, if you guys know what Raspberry Pis are. It's crazy. But the newer ones are like 100 times more capable. It's crazy.
Wow.
Yes, your question.
In my own studies of cryptography and cryptology, I went out and got a master's back in 2011 to 2013. And during that time, we studied a lot about cryptography and now I'm drawing a blank. When you embed images into common looking photographs and things like this, I forget what the name of it is, but we did that too. But my point is one of the odd things that I found out that just kind of really expanded my horizons was the contribution of the Arabic speaking world. And there have been things I still claim not to fully understand it, but if people want the background documents on this, just send me an email to williamslater@gmail.com, and I'll happily send those as attachments. But apparently, when they've got really serious about cryptography after 9/11, they they were exploring all these people that had contributed to the field, and they were actually shocked to see how deep some of the Arabic-speaking contributions were. And I don't know how many. I'm pretty ignorant about. I could speak some Arabic. I've gone to the trouble to learn some Arabic and be friendly with Arabic-speaking people. But if you pick up an Arabic book, it's got all these curly, wavy characters in it. But in the Western speaking world, we open a book and we start reading from the upper left side of the page all the way down to the bottom, and then we turn the page and go, top left to lower right. And that's how we read in the Western world. The Arabic speaking people don't read books like that. They start at the back and read from lower right going up to upper left. And so it's just a different way of thinking. But I've done a little cryptanalysis too, but I'm just fascinated with the contributions of Arabic speaking people in the whole cryptanalysis deal. And some of y'all may really want to see it.
Okay, good. Thanks for the comment.
Pavel, real quick, are you in Warszawa?
Yes, I'm in Warsaw now, in Poland.
Yeah, my wife is from there, and
Oh.
I spent my gosh, I spent about 20 different Christmases in Warsaw, starting in December 2000. They lived over in the Saska Kempa district, and
Oh, it's possible that you spent here more Christmas than I, because I'm originally not from Warsaw. I'm
yeah,
from another city. I came here to study at the University of Warsaw in 2004 and stayed here for almost 20 years.
sure.
But then my family moved to Krakow, another city in Poland, and now I spent most of my Christmas there.
It's my adopted country. I can't say enough good things about Poland.
Great, fantastic. Yeah, I also like living here, so I had many opportunities to go abroad and work in other countries, and I did some internships abroad in the US as well, but eventually decided to stay here in Poland. Oh, thanks, Bill. Very nice. Oh, I see some photos from the old town. Yeah.
Yeah, I think, matter of
Yeah.
fact, for those of you who like Poland and the Polish military, I was over at the Polish National Museum of Military History,
Mm-hmm.
and the one of the curators over there was a friend of my wife's, and she knew how much I loved. She knew I was an old Air Force officer, so I'd been going there for 13 years, and every time I would see this MiG-29, I would just drool, because oh my God, this is a top flight Russian fighter. So one day she surprised us when I was over in Poland for Christmas. She allowed me to sit in a Flogger and also the MiG-29. So I've actually sat in the cockpit of a MiG-29, and there's pictures of
Oh,
me in there. If you go into the 2012 series of pictures, but I'm real proud of that because there's a lot of Air Force officers that would give some left part of their anatomy to do what I did.
oh, nice. Ah, so you're lucky because there are not that many MiGs in Poland left.
Right.
Yeah,
Well, yeah, this was on a static display.
yes, in the museum, yeah. Yeah, that's nice. Indeed, I know this. I know this museum. I visited it several years ago. So that was quite nice experience as well. Yeah.
I think I tipped
did.
the museum employees that actually opened that MiG-29 up for me. I think I tipped each of them a
Yeah.
100 zloty because
Yeah.
it was the experience of a lifetime.
Yeah. So indeed, so Polish army has a long history because you know the origins of the country is dated back to 966, so
Yeah, not
966.
yeah. That's actually that
That,
picture of
yes,
966 with
yes,
Poland getting baptized. That
baptized exactly. Yes.
yeah, that's on my website.
Yeah.
That
So yeah, so it's more than 1,000 years. So for more than 1,000 years, indeed, we had a lot of wars.
right.
So indeed. So many things to display in the museum.
Yeah.
Currently, you know, so actually all these, you know, army branches also work on post-quantum cryptography. This is a very important topic for the army, for the defense ministry.
Pavel, a lot of people associate Alan Turing with breaking the Enigma cryptography. He was the guy that built, designed and built the bomb machine
Yes.
that would work up until midnight. But what most people don't know is that the geniuses that broke the cryptography for Enigma were from the Polish Cryptography Bureau.
Indeed, I know they're from Poznań, another city
Right.
in Poland, and I know that they first cracked Enigma in 1932, and then just before the war, in August, so just a few weeks before the outbreak of the Second World War, they met with representatives of the French and British Army, and just they gave all they know to them, and thanks to that, Turing and other people in the Bletchley Park were able to you know, build a bomb and crack the Enigma again. So there is
Right.
a monument. There is a monument to Polish cryptologists in the Bletchley Park in the UK. This is true, but I agree that it's not that well known as the bomb machine designed by
And
Turing.
and the American cryptography secret that a lot of people didn't know about until 1999, when so much of it got declassified, was the Navajo code talkers. And so, and it's real curious because they were brought in. They needed them very badly because we had broken Orchid and Purple Japanese cryptography schemes.
Mm-hmm.
But the most important thing when you're in a conflict environment on a battlefield is the safe passage of reliable communications. And so somebody got the bright idea to bring in these Navajos, and they came up with their own code, but they were using Navajo words to describe these things. And so every squad and every unit, the crypto squad, would have 3 people. It would have a radio operator, it would have the Navajo code talker, and it would have a guy who was the leader of the group that had a 45 pistol. And the reason for the guy with the 45 pistol is he was under orders to kill the Navajo code talker if they ever got captured, because they didn't want the code to get out. And they were successful. The code never got out. And so that helped them win the war in the Pacific. It's not well known, but the Marines could not have been as successful as they were without the Navajo code talkers. And the most recent ones died in the last couple of years. But they carry on that tradition into the Korean War and also into Vietnam I think it ended in Vietnam, but they kept it very classified until about 1999. And now, if you go do an internet search, you will see that the Navajo Code Talker Museum is on the web, and I've been a contributor to it because I believe in what they did, and I'm part Native American myself. I'm part Cherokee, but when you go to that part of Arizona and you ask around and you talk to people, you will find the grandchildren of those code talkers. And everybody that has any connection to a code talker is considered to be almost a celebrity because it was like a delayed honor given to those people. They were fantastically patriotic.
Mm-hmm. Great. Fantastic story. Nice. So Helen, I think it would be good to invite Javier once again to and ask him to give more details about these PQC algorithms. Indeed, this is very relevant, and there are already recommendations to make transitions from the contemporary cryptography algorithms to PQC. I know that some companies has already done it, like Google. And here in Europe, in the European Union, it's also recommended to implement this standardized quantum safe algorithms by 2030. And I heard that some countries even start recommending to do it, to complete it even earlier, because the progress, the pace of progress in the quantum computing domain it seems to accelerate. So thanks to AI in particular. So.
Here in America, I don't know if you guys have it in Poland, but here in America, there's a lot of dynamics in the job market, and who gets promoted, who gets a job, on and on. But the problem is that they've done enough research to know that an average PQC project is going to take anywhere from 3 to 7 years. But the career lifespan of a CISO, who's probably going to be the sponsor of the project, the career lifespan of a CISO is somewhere between 30 months and maybe 48 months, and that's it. That would be a long CISO, 48 months. So the problem is, how are you going to get people to be the sponsors and accept the responsibility of pushing through a PQC migration when they probably won't even be there when it gets completed? It's very messy.
Yeah.
And I don't know what the answer is, but my friend Roger Grimes, who's a well-known cybersecurity writer, and he's actually written a book on PQC. He likes to say, he said this back in May or April, he said, 5 years from now, there will be two types of companies. There will be companies that made the conversion and they'll be doing okay. And then there will be companies that didn't start soon enough, or they didn't take it seriously, and they will be out of business because their secrets will be being exposed. And back in May, one lady took it a step further. May or June, she said, her name is Louise Davy, and Helen, we ought to get her to come in and be a speaker. She'll blow you away if you hadn't heard her. She gives speeches about how to talk to the board about PQC, on and on. But she says, we're past that point where people didn't listen to us about PQC roadmaps and projects and things like this. So now we have to accept the fact that there's going to be some people left behind, and there are going to be some people that have to pay the consequences of not doing this. And we'll just have to look back and say, sorry, we tried to warn you, but you didn't listen to us. So we're going to have to accept the fact that you're going down in flames because you didn't listen. Pretty scary times.
Yeah.
So,
Yeah,
Helen, do we meet tomorrow?
Yes, tomorrow at 2 p.m.
Okay,
with
so
another topic.
yeah, your 2 o'clock is my 1 o'clock, so I'll be ready at 1 o'clock when you guys meet.
Great. And by the way, I've just read, I think that someone has said it, that just recently one of the AI models from Anthropic released or found a vulnerability in the Hawk algorithm that was considered as one of the PQC standards.
Right.
Yeah, it was just a few days ago. And the authors of Hawk decided to just remove it from the NIST contest. So it's not considered as for standardization anymore. It can happen. So as I said, AI can help in both in finding better algorithms, but also finding some vulnerabilities.
Oh, Chuba asked what algorithm? ELK? Hawk algorithm.
Hawk, yes, Hawk. Yeah. I'll try to find the announcement. Yeah, you can find the announcement on the official NIST website. I'll just share a link here. Yeah. Anthropic announced that it used an AI model to discover a vulnerability in a lattice-based digital signature algorithm called Hawk, which was under consideration for standardization. The Hawk development team subsequently withdrew its algorithm from consideration, and it will not be standardized or deployed. Very interesting.
Well, then the number they put on that announcement was, they said we should all be worried because Claude cracked it in 60 hours. And I think they said that 60-hour of compute time was worth like $100,000. But the thing is that people have been saying for years that if the bad guys could really crack classical encryption very well, then we would have, a lot of secrets exposed right now. But quantum computing is going to help us do it better. But the thought of cracking something that was supposed to be very robust in 60 hours of compute time, that should get all of our attention. And the guy actually said it's going to stress the importance of crypto agility. And he said, last month you could have used the excuse that we think all of our cryptography is safe because we don't know any reason why it shouldn't be safe. He said, now you can't say that anymore. Now what they're saying is you better get very creative about testing cryptography once that it's in and implemented, because if you don't, some guy's going to come along with an AI and break the cryptography, and there you will be. Helen, it might be a real good idea to have a group of people contribute, like instead of a 1 hour, 2 hour presentation, maybe like 15 or 20-minute segments about things like cryptography and cryptanalysis and cryptographic history, because I think that would be so diverse that it would get a lot of people's attention, and people seem to find this to be a infinitely interesting topic.
Oh, I will invite Dr. Javier to come back for part 2.
Good.
It'll be great. Yeah, I know I'm going to invite Jeremy to see if he can talk about his book.
Okay.
And Pavel, you should brief us about your understandings of the Polish Cryptography Bureau, because I think those guys were more. I think they were much more important, dedicated to intellectual excellence rather than beating on their chest and talking about how great they were.
So actually, I think I can try to invite a very good speaker for this, because there is one researcher from Poland. His name is Bartosz Naskręcki. So he's also from Poznań, so from the same university where these cryptologists who broke Enigma were affiliated before the war. And now he's also working on post-quantum cryptography, actually, but he also very closely collaborates with OpenAI. And he has a special access to the most advanced AI models. And I know that he employs them to, solve some mathematical problems. And I believe he could be a great speaker here. I can ask him, actually. Helen, if you're interested, I can do it.
Yeah, sure. Please invite him. Yeah.
Okay, good.
And Chuba got a comment. It doesn't seem that crypto agility gets rid of the risk of harvest now, decrypt later. Any question, comment about Chuba's comment about the risk of harvest now, decrypt later?
Yeah, so the risk exists, right? Because the idea behind harvest now, decrypt later, is that we get the data that we have now, or harvest the data that we have now, and they can be decrypted later. While crypto agility rather just focuses on the ability to update the cryptography mechanisms, let's say. But if something was harvested now, then even if we update it later, then someone will have access to the version that is already not secure enough. So this is true that it doesn't solve the problem completely. It just helps us. So it helps in a sense that maybe it gives more time. No, thanks for the link, William.
Yeah, that crypto agility RFC 7696 that's now going on 11 years old, but still it's a starting point if you want to understand where the crypto geeks at the Internet Society were 11 years ago.
Okay, Peter comment with cryptography does not get rid of the risk. There's only reducing risk. There's always risk.
Yes. I think we can agree.
Although in the Air Force we had a joke. We had these our best computers we ran all our war plan stuff on, and our command control stuff would be inside this vault door, and for our data center underground. And so they had a notice on there. They said this door is rated at 12 man hours, And so I was a dumb lieutenant and I didn't know what that meant. And so I asked this captain I was with one time, I say, why do they say this door is rated at 12 hours? And he says, well, you have to put it this way. It would take 1 hour, one man, 12 hours to break through that door, or it would take 12 men 1 hour to break through the door. So a lot of times I look at problems like breaking ciphers in terms of that vault door I saw in the Air Force.
Mm. So William, did you